Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at the eigenvalues and eigenvectors of both discrete time and continuous time signals. So in this topic, we will examine the advance operator on discrete time signals and the differential operator on continuous time signals. We will contrast their behavior with the corresponding delay operator and the antiderivative operator. We will find eigenvectors for the first two, and we will also find null spaces of the first two as well. We will observe how we can use these eigenvectors to solve various equations. All right, let's start by considering the vector space of discrete time signals. Now here the delay operator, as you will recall, is defined as follows. The first entry is now 0, the second entry is the original value at the first entry, and so on and so forth. It essentially shifts all values in the signal forward into the future by one time step. Now, this does not have any eigenvectors or eigenvalues, because if the delay operator applied to x is equal to lambda times x, then we require that the signal on the left, which is the delay operator applied to x, that must be equal to a scalar multiple of the original signal. Now, if the original signal is not 0, then neither is the delay operator applied to x. That means if there's at least one non-zero entry anywhere in the signal, then the delay operator cannot be 0. Consequently, D does not have a null space that is anything more than just the 0 vector. Also, if lambda is not equal to 0, then this implies that x naught must be 0, because lambda times x naught must equal 0. But if x naught is 0, then that implies that x1 is 0. And if x1 is 0, that implies x2 is 0, and so on and so forth. Consequently, if lambda is not equal to 0, then this is true if and only if x is the 0 signal. And that doesn't count as an eigenvector. Still considering the vector space of discrete time signals, you will recall that the advance operator, on the other hand, shifts all the values one time step into the future. And so the signal at the initial time is now what used to be the signal one time step into the future. Now, this advance operator is going to have an eigenvalue of lambda if the advance operator applied to a signal is equal to lambda times that signal. And so therefore we must have the left-hand side equaling the right-hand side. Now, if lambda is equal to 0, then we require that the left-hand side equals the right-hand side, and that means that all values of the signal must be 0 with the exception of the initial value. So therefore, this particular signal is an eigenvector corresponding to the eigenvalue lambda equals 0, because the advance operator applied to this signal is equal to 0 times this signal. Now, if lambda is not equal to 0, we require that the left-hand side, which is the advance operator applied to the signal x, must equal lambda times the signal x, which is on the right-hand side. But wait a second. This says that if the initial value is 1, then x1 must be equal to lambda. But if x1 is lambda, then x2 must be lambda squared. But if x2 is lambda squared, then x3 must be lambda cubed, and so on and so forth. Thus, an eigenvector corresponding to the eigenvalue lambda, when lambda is not equal to 0, is the signal 1, lambda, lambda squared, lambda cubed, and so on and so forth. And that is, this is the geometric sequences, and these are the eigenvectors. First, let us find all solutions to the delay operator applied to an unknown signal x equaling a known signal x naught. Well, if x naught is this known signal shown here, it follows that all solutions to the above equation must be of the form: the first entry is some constant, it can be any constant. The second entry is the first entry of our known signal. The third entry is the second entry of our known signal, and so on and so forth. Here, c is an arbitrary scalar value. It's an arbitrary constant. Thus, you'll note that all solutions are of the form the vector on the left-hand side plus all scalar multiples of the vector on the right-hand side. But the vector on the right-hand side is in the null space of the advance operator, and the advance operator is the inverse operation of the delay operator. Sounds like differentiation and integration, and it should. Next, let us find solutions to this particular equation: the advance operator applied to an unknown signal x plus alpha naught times that signal x is equal to the zero signal. Well, substituting our eigensignals for the advance operator into this equation, which are, of course, the geometric sequences with a ratio gamma, then this must be true. But if we apply the advance operator to the geometric sequence, we just get gamma times the original geometric sequence. Now we can factor out the sequence of the geometric sequence. So we get that this is true if, well, that's going to be true if gamma plus alpha naught is equal to 0. Because if gamma is not equal to 0, then we require, for this equation to be 0, we require that gamma plus alpha naught is equal to 0. So, in this case, the only ratio that's acceptable is when gamma is equal to negative alpha naught. For example, given this equation, the advance operator applied to x plus twice x is equal to 0, in which case we note that if the signal is defined as negative 2 to the n, then the advance signal applied to this signal is indeed negative 2 times the signal. And thus, we get that the advance operator applied to this signal plus twice this signal is just essentially negative twice the signal plus twice the signal, which is equal to 0. Let's view this more clearly. The top signal here is just the signal negative 2 to the n. And we are multiplying each entry in that signal by 2, as indicated by having the 2 on the left-hand side. Onto this, we are adding the advance operator applied to this signal. Well, the advance operator simply moves all of the values one step into the future. Oh, wait a second. Twice 1 minus 2 is 0. Twice negative 2 plus 4 is equal to 0. Twice 4 plus negative 8 is equal to 0, and so on and so forth. So you can see that twice the first signal plus the advance operator applied to that first signal is indeed equal to the 0 signal. Let us now consider finding solutions to this problem. The advance operator applied twice to x plus alpha 1 times the advance operator applied to x plus alpha naught times x is equal to the 0 signal. Substituting in our eigensignals into this, we get the following expression. But, of course, if we apply the advance operator once to that eigensignal, then we just get gamma times that eigensignal. And if we apply the advance operator twice, we get gamma squared times that geometric sequence, where again the common ratio is gamma. So this is what we now have. We can now factor out the common sequence, and if gamma is not equal to 0, then the geometric sequence is not the 0 sequence. Consequently, for this to be equal to the 0 signal, it must be that the scalar multiple of the geometric sequence must be equal to 0. So we require that gamma squared plus alpha 1 times gamma plus alpha naught equals 0. That is, the ratio of the geometric sequence must be a root of the above quadratic. Now, however, let us consider this specific equation. All right. So a solution to this equation requires that gamma squared plus 7 times gamma plus 12 is equal to 0. So gamma can either equal negative 3 or gamma equals negative 4. Now, we note that if the signal x is such that the nth value is negative 3 to the n, then the advance operator applied to x is negative 3 times that signal x, and the advance operator applied twice to x will be equal to 9 times that original signal. Therefore, let us substitute this particular signal into this equation. Well, that essentially just gives us 9 times the signal plus negative 21 times the signal plus 12 times the signal equals 0, and we can see that that is indeed true. Note similarly that if we have the signal where the nth entry is negative 4 to the n, then the advance operator applied to that signal is equal to negative 4 times the original signal, and the advance operator applied twice to that signal yields 16 times that signal. Consequently, once again, given this equation, if we substitute in the signal negative 4 to the n, then we get that 16 times the signal plus 28 times the signal plus 12 times the signal is equal to 0, which again is true. Hopefully I said negative 28. Again, to view one of these, the original geometric sequence is 1, negative 3, 9, negative 27, 81, and so on and so forth. So I will take 12 times that. The advance operator applied once moves all time one step into the future, and 7 times that signal is the second signal there, plus the advance operator applied twice gives us the third signal there. You will notice that 12 minus 21 plus 9 is equal to 0 for the first entry. In the second entry, we have negative 36 plus 63 minus 27, and that again is equal to 0. And so on and so forth. You will see that each and every column adds up to 0. Next, let us consider the space of all continuous time signals, for example, y of t. You are already familiar with the linear differential operator. Now, for y to be an eigenfunction of this operator, we require that the derivative of y of t is equal to lambda times y of t. As you may have already guessed, the solutions to this are the exponential functions. So the derivative of e to the lambda t is equal to lambda times e to the lambda t. First, let us find solutions to this problem. The derivative of an unknown function is equal to a given known function. So, for example, find functions such that the derivative is equal to cosine of t. Well, that's essentially what we're doing here. We are finding antiderivatives of a given function. Now, from calculus, you know that if y0 is one antiderivative, then all antiderivatives are of the form this function plus a constant. So, for example, if y0 is cosine of t, then a solution to the derivative of y equaling cosine of t is for y to be equal to sine of t. However, sine of t plus 7 also has a derivative of cosine of t, and sine of t minus 500,287 also has a derivative equal to cosine of t. Here, c is an arbitrary constant. You will remember that it is the constant functions that form the null space of the differential operator. The derivative of a constant is the zero function, and the constant functions are the only functions that have this property. So this is just like the signal 1, 0, 0, 0, 0, and so on and so forth, forming the null space of the advance operator. Next, let us find solutions to this problem. Find me a function y of t such that the derivative of that function y of t plus alpha naught times y of t is equal to 0. Well, essentially what we need here is we need functions y of t such that the derivative is a scalar multiple of that function. So that makes sense to substitute in the eigenfunctions of the differential operator, that is e to the lambda t. So now we are trying to find solutions of the form the derivative of e to the lambda t plus alpha naught times e to the lambda t is equal to the zero function. But wait a second, the derivative of e to the lambda t is just lambda times e to the lambda t plus alpha naught times e to the lambda t equals 0. We can factor out the function, and now if lambda is not 0, The only way that this can equal the 0 function is if lambda plus alpha naught is equal to 0. Thus, the scalar in the exponent must be negative alpha naught. So the solution to the equation above is e to the negative alpha naught times t. For example, suppose we want to find solutions to the derivative of y of t plus twice y of t is equal to 0. Well, we note that if you let y of t equal e to the negative 2t, then the derivative of e to the negative 2t is just negative 2e to the negative 2t. Thus, we note that if we substitute this into this equation, we get negative 2e to the negative 2t plus twice e to the negative 2t, and those two cancel each other out, giving us the 0 function. So thus, yes, y of t is equal to e to the negative 2t is indeed a solution to the above equation. Next, let us find the solutions to this equation. The second derivative of y of t plus alpha 1 times the derivative of y of t plus alpha naught times y of t is equal to 0. Well, once again, it seems that we are adding functions that are similar to each other when differentiated. That means that we are adding eigenfunctions together. So let us substitute in e to the lambda t into this equation. Now, the second derivative of e to the lambda t is just lambda squared times e to the lambda t, and the derivative of e to the lambda t is just lambda times e to the lambda t. So let's substitute that in, and now factor out the function. Now, if e to the lambda t is not 0, the only way to make this the 0 function is for lambda to be a root of the quadratic on the left-hand side. So in this case, the quadratic is lambda squared plus alpha 1 times lambda plus alpha naught. Let's look at an example. For example, consider this equation. So now alpha 1 is equal to 7, alpha naught is equal to 12. Well, for e to the lambda t to work, lambda must satisfy lambda squared plus 7 lambda plus 12 is equal to 0, so lambda must be either negative 3 or negative 4. Let's try e to the negative 3t. So the derivative of e to the negative 3t is just negative 3 times that function, and the second derivative is just 9 times that function. All right, so there we have substituted e to the negative 3t into the original equation. When we calculate the derivatives, we get that 9 times e to the negative 3t plus negative 21 times e to the negative 3t plus 12 times e to the negative 3t is equal to 0. But that's true because the coefficients 9 minus 21 plus 12 do indeed add up to 0. You can do exactly the same thing with e to the negative 4t. Also, if you were to substitute something like just e to the t in the above equation, you'd get that the second derivative of e to the t, which is just e to the t, plus 7 times e to the t, plus 12 times e to the t, that's actually equal to 20 times e to the t, which is not equal to 0. So if you were to substitute e to the lambda t into that equation for any other lambda other than lambda equals negative 3 or lambda equals negative 4, you would find that the sum of the derivatives of those functions do not equal the zero function. Following this topic, you now understand that the advance operator and the differential operator have null spaces. You understand that the delay operator and the antiderivative operator have infinitely many solutions, and those include adding all scalar multiples of the null spaces of the corresponding operators above. You know that the geometric sequences are the eigensignals of the advance operator. We call them eigensignals instead of eigenvectors. And you know that the exponential functions are the eigenfunctions of the differential operator. We've also reinforced the understanding that an operator applied to an eigenvector results in a scalar multiple of that eigenvector. The derivative of e to the lambda t is lambda times e to the lambda t, and the advance operator applied to the geometric series with ratio gamma is simply gamma times that geometric series. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!